So welcome to the last talk of the quarters. Thank you for coming. Thank you for showing up to this in this very strange COVID year. Hopefully next year we will be back in person and with actual food and stuff. So that's that. And thank you, Gabriel, for agreeing to give this talk. And you can begin as soon as you want.
Great. Okay, so hello everyone. My name is Gabriel, and I'm going to talk a bit about topology and graph theory. I am not by any means an expert in the topic, but I'm certainly going to try my best. First, I'm going to start with the definition of a graph. So probably most of you already know what's a graph. So a graph is just an ordered pair, which we will denote in this talk by G, which is composed by the set B, which is a non-empty set of points, which we will call vertices, and the set E, which will contain subsets of vertices of the set of vertices, which we will call edges. So an example of this definition, for example, if our set of vertices is a set A, B, C, D, E, and our set of edges is this one right here, then the pretty thing about graphs is that we can like make a lot of nice drawings. So we just like draw down the points, and for each of the edges, for example, for the subset AE, then we draw an edge between the points AE, and so on and so forth, and we got ourselves a graph. So this is probably not the first time you guys have seen this. So graphs are somewhat present in our daily lives. So for example, in chemistry, we have like a useful representation of molecules as like graphs. So, you have like a lot of points joined by edges. Also, every time you log into Facebook, you have like these graphs, and each vertex is like a person in the world. And if these two persons are friends on Facebook, then you have like an edge between them. Also, for example, in arrow routes, vertices are placed in places all over the world. And if there's a flight connecting these two places, then you have like an edge between these two places. So basically, this is what graphs are. But now I'll talk a bit about how these graphs come about. So some historical context. So it was around 1679 when Leibniz wrote a paper where he was sort of concerned because he said there was a mathematical area that had been completely unexplored. So the areas that were being studied at that time were geometry, since the Greeks, algebra, and arithmetic. But Leibniz was concerned with a special area which deal with not magnitudes, but just position. He said particularly that algebra didn't produce either the shortest proofs or the most beautiful geometric constructions, and he called this area analysis situs. Historians don't really know what he meant by analysis situs. Some think he meant linear algebra, others topology, but there's not really a consensus. So then some years passed, and the Königsberg bridge problem appeared. Nobody really knows where it came from, but Königsberg was a city previously in Germany, now in Russia, and it was a city that was divided into 4 places, and these 4 places were connected by 7 bridges. So people had a lot of trouble solving this problem, and it was widely known that Euler had the solution to this problem. So the solution seems to be really short. So we can represent each of the places on this map with one vertex. And for each of the bridges between the places, we can draw an edge. So the solution that Euler gave was that, let's say, for example, you start in this vertex and you move to this vertex. So the conditions that the problem posed were if you made the walk in these like bridges and places, you have to go through all 7 bridges only once, and you have to go back to your starting point. So if you start in this vertex here, and you're gonna go to this other vertex over here, then you need to go out of this vertex. So let's say we then take this bridge. If we need to cross all bridges, then we go to this other bridge over here. But since we cannot cross one same bridge twice, then we're stuck. And basically what this tells us is that the solution to this problem is that such walk doesn't exist, such path doesn't exist. So yeah, this is like basically the solution. We solved it in like 2 minutes, but people took a really long time solving it like a while ago. So for a bit of history, some mathematicians sent this problem to Euler, and he replied with the solution. And what he said was that he was surprised because this problem required no mathematical principle to be solved, like counting or algebra or anything really, but just like pure reasoning. That's what he said in the beginning. But then he wrote himself a letter to another mathematician who was a bit more acquainted with the geometry of position or analysis series. And he asked if this problem or this mathematical area had something to do with that geometry of position, because he didn't have to deal with any magnitudes, but just with the position of vertices in our map. So after this, graph theory was born, but not only was graph theory born, but also topology was born. Actually, topology went on as analysis series, but it was not until years later when some group of mathematicians decided to call it topology. Then Poincar published his work Analysis Series, where he laid the foundations of algebraic geometry, of algebraic topology, and then it was Hausdorff in around the 1900s when he published his book Basics of Set Theory, where he defines formally for the first time what a topological space is, and like he develops this theory that was previously called analysis series. So this is how all of this came to be. So now I will define what a topological space is. So a topological space is nothing more than a pair with a set X and a collection of subsets of X T, or we will call it T, such that the following properties are satisfied. So the set itself must belong to the collection of sets, to the topology. The empty set must also belong to this collection of subsets. Also, if we have two elements of such collection, then the intersection of those two elements must also be an element of the collection of subsets. And if you have a subset of the elements of the topology, the union of all those subsets must also be an element of the topology. If you've taken, I don't know, like Calc 3 or Calc 1 in IVL, in the IVL version, you know that when we define open sets, we find out that open sets are the sets that satisfy these three properties. So this collection T is called the topology on the set X, and the elements of that topology are called open sets. When we study open sets, for example, in Euclidean spaces, that's just a particular case, but this is like extended to this general definition. So I'm going to give some examples of topologies. So for example, if you consider the power set of a set X, that is the collection of every subset that you can create from some set X, then that collection is called the discrete topology. And you can check that this is indeed a topology with the properties I mentioned before. And for a second example, we have the indiscrete topology. And this is the collection of the set itself and the empty set. And it's sort of the opposite of the discrete topology, and it also satisfies these properties. But to give some more interesting examples, let's say, for example, we have a set with the elements A, B, C. So we can create a topology by considering the subsets A, AB, and ABC. The interesting thing about this topology, as a first example, is that if you want to work with the element B, by force, you're also working with the element A. So like the element A goes on its own, but if you want to do something with the point B, you need to also consider the point A. For a second example, this is not the case. You have points A and points B on their own. But if you want to consider the point C, then you also need to consider points A and B. So this is interesting because in the end, what we are doing here is sort of gluing points together, which is the main idea of graphs. First, before connecting these two ideas, I'm going to talk a bit about how topologies are defined from metric spaces. So if you have a metric space on a set and some defined distance, then the collection of all open sets that you have defined with respect to these metrics will form a topology on X. But how do we form this topology on X with the metric space? So this comes out when we consider balls, open balls, and a ball is just the set, B, a ball centered at the point X with radius R is the set of all points Y, such that the point Y is on the set X, and the distance between the point X and the Y is less than the radius R. So basically, this is an open ball. For example, in Euclidean spaces, we can define this distance as the norm, and that's how we have like open balls in Rn. And then when these open balls satisfy two important properties. So if you consider the collection of all balls in your metric space, then every point in the set X will be contained in an open ball. So basically all space is contained or is covered by open balls. So that is one of the properties. And the second property is that if you have two balls and there is a point in their intersection, then there is another ball that will be inside that intersection. So this helps us construct like a more general idea of topologies. So here's a theorem. If you have a set X and a collection of subsets of this X, consider another collection of subsets such that if the union of the elements of B is equal to your whole set, and if you have two sets of that set B, if there's a point in their intersection, there will be another element of B that will contain your point X, and this will be contained in the intersection of the first two elements. So this is basically doing the same as open balls. So the union of all open balls covers the complete space. And if you have two balls and point in their intersection, then the smaller ball will contain that point and will be like inside the intersection of those two initial balls. So this will form a topology which I describe here, which is all subsets of X, such that if you have a point on that set, then there exists an element of your basis B. We will call this set basis, and such that every point in that element of your basis will be a subset, will be contained in a subset of your whole set. So for example, if we are talking about Euclidean spaces, we can have like this set here, and we know that this is an open set. Like in Euclidean spaces, we define that this set will be an open set if for any point inside this set, you can find an element of your basis that will contain such point. In Euclidean spaces, for example, we consider these elements to be like open rectangles, which we form by the Cartesian product of intervals. So this is a quite neat way of constructing topologies with fewer sets. Before going further, here's an example of how we can form a topology with a basis. So there's a very known form of constructing a topology in the set of integers. So if you consider the set of integers and define the metric in this set, as in, for example, the distance between the point -6 and -4 is just 2. When you have this metric, then you have open balls. And if you have open balls, then you have a topology. But the thing about this topology is that you have every point as an isolated open set. So this topology is disconnected. So like points are on their own, and there is no way of having them connected. But Kalimski's line, or the digital line, gives us a basis B, which we'll consider as basic open sets, the odd numbers. So you have like these odd numbers on some open sets by themselves. And for all even numbers, you will consider their closest neighborhood. So the open set that will contain even numbers will be this neighborhood that has the previous and the next odd number. What this topology does is that it connects like the set of integers, and if we look it from afar, it actually looks like a line, and this topology is connected. So this is another way of how topology allows us to connect points, and this will actually come about when we talk about the solution to the main problem we will pose. Another thing about the digital line is that when you take the Cartesian product of the set of integers with themselves, then you can construct the digital plane, which is this basic idea. You just take, for example, the Cartesian product of of odd numbers with odd numbers, and of even numbers with odd numbers, and even numbers with even numbers, and you get like a plane which has like maybe like squares as open sets, line segments as open sets, and points on their own as open sets. And this allows us to talk about a plane that has connectedness in its topology. A professor from a university in Mexico went to a congress which talked about like combinatorics and topology, and she was wondering the following problem. If you have a graph G, is it possible to define a topology in the set of vertices such that the fundamental structure of the graph is preserved? That is, we're looking for a way of translating the idea of a graph and the way it's connected to maybe topological / geometric representation. And there's actually maybe easier way of doing this, or one which is widely known between mathematicians. So if, for example, you have like this graph, you have like this graph, you can put this graph on the plane, and this this graph will inherit the topology of the plane, because the plane already has a topology, and voila, you have this graph with a topology, with an inherited topology. But this was not quite what we were looking for, because if you consider the topology on this graph, you have like infinite points in these line segments, and initially graphs are like finite objects. So you have only like 4 points and edges that didn't really mean points in the topological sense. So that was one way in which this solution didn't work, but still it's a really important solution. So I will mention it briefly. This solution is called the geometric realization. So if you consider a graph with a set of vertices and a set of edges E, first we will assume that it is finite. This is also possible with infinite graphs, but for the sake of this talk, just consider then the space Rn, and we will make the following mapping. So for every vertex on your graph, you will map this vertex to the vector on the standard basis of Rn. And for all vertices that are connected, you will draw a line segment between these two vectors from the standard basis. So for example, I'm going to draw a graph with 3 points because I cannot draw beyond R3. But so if we have, like, for example, this graph with 3 vertices, say this is the vertex B1, B2, and B3. So when we consider the space R3, you consider the standard basis. So this is the vector E1, E2, and E3. And when you make the mapping I mentioned, so for example, the vertex 1 is connected with the vertex B2. So you make a line segment here, and B2 is connected with B3. So you make another line segment here. So this is called the geometric realization of a graph, and it is quite a nice solution. But again, it is not quite what we were looking for, because you have still infinite points here and also here. So that's one of the issues with this solution. But the second issue with this construction is that it doesn't work as well when we consider multigraphs, which I will define in a couple minutes. And it also doesn't work quite well with graphs with loops, which I will also define. And one of the problems which some mathematicians consider to be the biggest problem was that if you have non-isomorphic graphs, this can translate into homeomorphic geometric realizations. So for example, if you have a graph with 2 vertices, then the geometric realization of this this graph is just this line segment in the plane. But for example, the geometric realization of this graph here, if we label these points as B1, B2, and B3, is the same geometric realization I showed here. But the thing is, like, if you unfold this like line segment here, you still get like a straight line. And for the topology, these 2 segments represent the same thing. So this solution doesn't preserve this this special feature of graphs. So we still need to look for something else, at least for this purpose. So then we pose the following problem, which is like the complete version of what I've been talking about. So given a graph, can you define a topology such that the graph G will be connected if and only if the topological space is connected? Because it can also occur that your topological space will be disconnected. So that's something we want to rule out as soon as possible. The second condition is that if your graph G is isomorphic, then your topological space will be, well, your topological spaces will be homeomorphic. So like between two graphs, if you can make a mapping between the vertices of two graphs, then the topological spaces will be homeomorphic. And finally, if H is a subgraph of a graph G, then the topology of the graph H will coincide with the inherited topology of the graph G. Just to make sure, a subgraph of some graph is a graph such that the set of vertices is a subset of the set of vertices of the original graph, and same for the set of edges. So mathematicians first wondered if we could try, for example, these two graphs over here, and if we want the topology to be connected, then if this point, for example, in this graph is connected with these two other points, then the basic open set of this graph should be, for instance, this set here, right? And because the graph is symmetric, then it holds for all the points here. So, okay, it might work for this graph. But then if we consider this graph on the right, then we know that this is an open set from the previous graph, but we also know that this is an open set. So then the intersection of open sets is also an open set. So we run into a problem because this new subset here is also an open set, but this open set did not appear on our original graph. So moral of the story, it seems like it's not possible. But then instead of just considering the set of vertices on graphs, mathematicians decided to consider the union of the set of vertices and the set of edges. And it turns out that we have, in some cases, two solutions, and in more cases, quite a few solutions. So they did this for graphs and multigraphs. So first I'm going to define what a multigraph is. So a multigraph is an ordered triple, which will be formed of the set of vertices, the set of edges, and the function f, which will go from the set of edges to the power set of the set of vertices. So it will map an edge with a subset of two or less vertices. So the cardinality of each element of the function will be less than or equal to 2. So for each edge E, we will map it to the function, to the element Fe, which will be a subset of the set of vertices, and this element Fe will be called the end nodes of the edge E. If the cardinality of Fe is equal to 1, then we call that edge a loop. We will see why right away. And if the function f is an injective function and has no loops, then this is just the definition I gave in the beginning. So it is a graph in the original sense. So as an example, let's say we have the set of vertices 1 to 3, edges A, B, C, D. And so the function maps, for example, the edge A with the vertices 1, 2. So we have this edge here. The edge B also with the vertices 1, 2, the edge C with vertices 2, 3, and the edge D just with the vertex 3. So these are called multi-edges, and these are called loops. And this is what our original definition didn't account for, but will be useful for the solutions we will find out. So the first solution people found out was the digital topology of a graph, which is like really close to the digital topology I defined before. So given a multigraph, we define this topology D on the union of the set of vertices and the set of edges. as the topology which will be generated by this basis. So this basis has as basic open sets the vertices themselves, and then it also has as open sets the edges that connect with their end nodes. So for example, these are like the odd numbers in the digital line, and these are like the even numbers. So the edges will be connected with the points they are connected to, with the vertices they are connected to. This topology is called the digital topology, and we will denote this topological space by DG. So how do we visualize this topology? So for example, consider this graph here. I will draw each of the edges just like an X for the sake of the drawing. So as I mentioned, the basic open sets are the vertices themselves. So we have these open sets, and then we have the edges with the vertices they are connected to. So we have these open sets here. So it turns out that this topology does satisfy the properties we were looking for. And it is a solution then to the problem we posed. Then we have another solution, which an author called the octopies topology, which we'll see why he or she called it this way. So again, given a multigraph, we define the topology P on the set of the union of the set of vertices and the set of edges. And this topology will be generated by the basis, which is formed by the edges as basic open sets, and then as vertices with union the edges that inside in that vertex. So for example, if we look at this vertex here, the open set of this vertex will be all the edges that inside in that vertex. This is probably why the author calls it octopies topology, because it looks like an octopus. But for a more general example, let's say we have the same graph we looked at before. So the basic open sets are the edges themselves. And then if we consider vertices, we have to consider the union of the vertex with the edges that are inside in it. So the open sets we have are this. For this next vertex, we will have this open set. And then for this vertex, we will have this other open set. And you see, we have like those octopies shapes, and this is why the author calls it that way. So just to wrap this up, this was initially made by a mathematician Antoine Bella as his PhD thesis from the University of Waterloo in 2005. And in this thesis, he writes the following theorem. So given a graph, just a graph, he didn't really work with multigraphs. Then if we consider the digital topology, then the graph indeed will be connected if and only if the digital topology is also connected as a topological space. Two graphs will be isomorphic if and only if the digital topological space of those two graphs is homeomorphic. And finally, if we have a subgraph H of some initial graph G, then the topological space of the subgraph will be a topological subspace of the topological space of the initial graph. This result also holds for multigraphs, but still he didn't go into them for a reason I will mention right now. And this theorem also works for the octopies topology. So the result also holds here for multigraphs. And to wrap this up, one of the next theorems he shows is that given a graph, the topologies, the digital topology and the octopies topology will be the only two topologies that satisfy the desired properties. So if you try to define another topology, you will run into problems, and some of the features you want to preserve will not be preserved in the end. So this is the reason why he didn't go into multigraphs, because if you consider multigraphs instead of just graphs, this result also works for multi-edges, but it doesn't work when you consider loops on vertices. If you consider loops, then you can have like quite a few more topologies, which are also classified already. But this is initially what was proved by Antoine Bella. And that was it. Thank you very much.